So we want to make sure we're comfortable working the problem that lets us calculate the net electric field at a point in space due to a series of point charges. The nice thing is that, again, this is just a vector addition problem, and hopefully at this point we're pretty comfortable working vector addition problems. The only details that are meaningfully different are we just need to pay attention to what's the direction of the contribution from each particle to the electric field. So does it point towards the particle or away from the particle? And then how do we calculate that magnitude? The rest of this process should at this point seem pretty familiar. So what we're going to do is work a problem like this. So here we've got two charged particles that are fixed in the XY plane. Particle 1 carries a charge of -2 nanocoulombs and lies along the positive x-axis 4 meters away from the origin. Particle 2 carries a charge of +5 nanocoulombs and lies 3 meters directly below particle 1. What's the magnitude and direction of the net electric field at point P, which is located at the origin of the given coordinate system? So we're interested in the net electric field created at the origin due to these two source charges. So the first thing we're going to do is go ahead and label the signs of these just to make sure that we keep that clear as we're going through and setting up our work. So the first particle is negatively charged. The second particle is positively charged. So we'll go ahead and draw that onto our picture. And then there's some basic geometry that we want to go ahead and make sure we know what those values are. Mostly we need to know the distances from the charges to the point P. So for particle 1, we were told it's 4 meters away from point P. For particle 2, we were told it was 4 meters across and 3 meters down, which means I'm going to Pythagorize those two numbers. And so the square root of 3 squared plus 4 squared says that charge 2 happens to be 5 meters away from point P. And then again, because I know that the electric field vectors are going to lie along the lines that connect the particles to the point, it's probably also going to be useful to go ahead and define this angle theta here. That's the angle between the line that runs between charge 2 and point P and the x-axis. And so again, inverse tangent of opposite side 3 meters, adjacent side 4 meters tells me that that angle happens to be 36.9 degrees. So with that information in hand, I want to go ahead and set up the vector diagram. So there's two charges here. Those two charges are going to both make a contribution to the electric field at point P. Charge 1 is negative, so it's going to have a contribution that points from point P towards that charge, so it's going to point to the right. Particle 2 is positively charged, so the electric field contribution at point P will point away from particle 2, so it's going to point up and to the left. So here are the two individual contributions. These are the vectors that I need to add together. To do that, I'm going to pick a coordinate system. I'll just use the one that I've been given. And so that angle theta, again, we see pops in. It in our vector diagram here is the angle between E2, the electric field vector due to charge 2, and the x-axis. So if here are my two vectors, to add them up, I know I need to break them up into components, so I'll go ahead and do that. Again, the contribution from charge 1 points along the positive x-axis, so it's going to have a y component that's 0 and all the magnitude is going to be in positive x. For E2, again, it points up and to the left, so it'll have a negative x component, a positive y component. That angle theta is between the vector and the x-axis, so cosine theta is going to go with the x component, sine theta is going to go with the y component. So my two components for E2 are negative E2 cosine theta for the x component and positive E2 sine theta for the y. I don't know anything about the net electric field, so I'm going to choose to leave that vector in terms of its x and y components, which is what I've done in my table. Use the table to set up my two equations. And so again, I know that the equation on the left is going to give me my x component equation. The column on the right is going to give me my y component equation, and so I can set those up. So E1x plus E2x equals the x component of the net electric field. That's E1 plus negative E2 cosine theta. Because again, I'm adding them together, and that component happens to be negative. Add those two together on the left, that gives me the x component of the net field on the right. For my y component equation, E1y plus E2y equals the y component of the net electric field, and again 0 plus E2 sine theta equals the y component of the net field. So now that I've got my two equations, again what I see is I know the angle theta. My x and y components of the net field are my two unknowns. I've got two equations with two unknowns, which means those are the only two that I can really have, which means I need to figure out what the magnitudes are for E1 and E2 so I can plug those in, and that's easy enough to calculate using my KQ over R squared equation. So I'm going to do this twice, once for particle 1, so E1, its magnitude is going to be K times the absolute value of Q1 over R1 squared. So K, I know what its value is, 8.99 times 10 to the 9th. Go ahead and plug that in. Q, again, I want the absolute value, so I don't worry about the minus sign here. So when I plug in Q1, it's just 2 times 10 to the minus 9. The times 10 to the plus 9 and times 10 to the minus 9 actually cancel out here, so I end up with something that's relatively normal as a number. And then the distance from particle 1 to point P is 4 meters. So 4 meters gets squared on the bottom. Plug all that in and I get 1.2 newtons per coulomb, knowing that that's my SI unit for electric field. Do the same thing for the magnitude of the electric field vector from particle 2. So again, this is going to be KQ2 over R2 squared. K, same value. Q2 is 5 times 10 to the minus 9, and the distance from particle 2 to point P is 5 meters, so 5 gets squared in my denominator. Plug all those into my calculator and I get 1.80 newtons per coulomb. So now that I know the two magnitudes for E1 and E2, I can come back and plug those into my two component equations. So plug it into X, solve for what the X component of the net electric field is. I get negative 0.315 newtons per coulomb. Plug E2, its magnitude, into my y equation, and I get that the y component of the net electric field is 0.08 newtons per coulomb. So that tells me the simplest way to report what the net electric field is, of course, now that I know the components, is just to report it in terms in unit vector notation. And so x component I hat plus y component j hat. Plugging in those values, I know that the net electric field as a vector is negative 0.315 newtons per coulomb I hat plus 1.08 newtons per coulomb j hat. And so again, I can easily draw that in, right? So that I know that the x component being negative tells me it's going to point back to the left. The y component being positive tells me it's going to point to the right, or the y component is going to point up. The y component, its number is certainly larger than the x, roughly by a factor of 3, and so that means it's pointing up about 3 times more than it's pointing to the left. Well, once I know the components, of course, I can go ahead and get the magnitude and direction of the net electric field. And so to get its magnitude, I'm going to Pythagorize, so x component squared plus y component squared, take the square root. When I do that, I get that the magnitude of the net electric field at point P is 1.12 newtons per coulomb. And again, if I want its direction, well, I'll label this angle theta here as the angle that the net electric field vector makes with the x-axis. Again, I recognize that because my x component is negative, that's an angle that's being drawn with the negative x side of the axis. So I'm going to take calculate phi by taking the inverse tangent of y component over x component. My calculator tells me that's negative 73.7 degrees, and so I know that really what that means is, in this case, it's 73.7 degrees above the negative x-axis. So again, vector addition problems are what we're going to do to calculate the net electric field at a point due to a series of point charges.